Key principles of machine learning, often referred to as ML, are fundamental to understanding how artificial intelligence is generated. ML is currently the most widely used approach to creating AI. The ML toolbox is large and constantly expanding, so it's really helpful to structure it. We divide the various ML methods into three types: supervised learning, unsupervised learning, and reinforcement learning. Depending on which type you choose, there is a fundamentally different approach to training an AI model using an ML algorithm. In the following sections, we will also discuss the problems for which these types are suitable. Supervised learning is a type of learning that requires both the inputs and the expected outputs in the training data when developing a model. In supervised learning, these consist of data pairs, the input data and the corresponding label. The label is the desired output that the model should learn for the input. The term annotation is also often used in this context. Although the terms labeling and annotation are often used interchangeably, annotation is a special case of labeling. Imagine a supervised learning scenario, an AI that is used to sort apple varieties. The training data consists of images of different apples and the corresponding labeling of the variety. If this label is missing from the data set, it usually has to be added by people who are familiar with the subject. This can be very time-consuming. In the training phase, the ML algorithm adapts the model to the training data. In this way, the model gradually learns to represent the relationship between the input data and the specified label. The aim of the training is for the AI to learn the underlying patterns between input and output, which can be transferred to new but similar input data after training. The training data set must be sufficiently large so that the correlations can be learned by the AI. The training dataset can contain a few hundred to many thousand or even millions of data points depending on the task. After training, the model undergoes a final evaluation. This involves presenting the ML model with previously unknown data to test how well the model can make predictions with the new data. Ideally, an AI is trained until the accuracy of the AI's predictions meets the requirements. Supervised learning is a particularly good choice when the problems to be solved are classification or regression tasks. What is classification? The supervised learning example just described is a classification problem. There is one class for each type of apple. In general, classification is used to assign input data to a fixed number of classes. An input data, for example, the image of an apple, must be only ever assigned to one class, such as an apple variety. The number of classes is small compared to the amount of training data. Only classes that are sufficiently represented in the training data can be learned in the training phase. The following problems are well suited to be solved with a classification algorithm: object recognition in images, face recognition in images, spam filters, brake assist from distance sensors, or maintenance recognition of a vehicle. What is regression? In contrast to classification, regression is not about assigning two classes, but about estimating a numerical value, such as estimating the sucrose content of apples based on various input characteristics like size, color, or time of harvest. Other examples of tasks in which regression is used include predicting a person's age based on data about their habits, prediction of future share prices, or estimating house prices based on house size, number of rooms, location, year of construction, etc. You have to be careful with the term regression. In the testing context, regression also occurs in the term regression test. Regression tests are used to determine whether existing or new error states can be detected elsewhere after a change in the software. Regression in the ML sense and regression tests are therefore terms that fundamentally describe different topics. Unsupervised learning. If the data is not divided into classes in advance, unsupervised learning algorithms can still find similarities among the input data. During the training phase, the learning algorithm finds patterns in the data and deduces similarities. The learning algorithm adapts the model so that it can sort data according to similarities based on the features. Concerning our apple example, images of fruit varieties could be grouped based on similarities or differences in shape and color. In this case, the algorithm could not specify the type of fruit itself, but the main distinguishing criteria. As in supervised learning, the training phase is followed by a test phase. In this phase, the model is presented with a new set of previously unknown data, which it has to assign to the groups it has learned. The model is trained until the accuracy of the assignment is satisfactory. We know two approaches: cluster formation and association in that field. What does cluster formation mean? This type of machine learning, also known as clustering, searches for subgroups within a data set that have similar characteristics or properties. Clustering is used for problems in which groups of input data points with similarities are to be found. For example, categorize different groups of customers for different marketing purposes, or finding patients with similar clinical pictures for a common diagnosis. The k-nearest neighbor and k-means algorithms are particularly well known for clustering algorithms. The problems often relate to high-dimensional data sets, meaning data in which each data point is assigned to a large number of values that we as humans can no longer keep track of, like the expression of genes in a cell. What does association mean? Algorithms from the field of association can be used to solve tasks in which relationships and dependencies between characteristics within a dataset are to be found. Association algorithms are typically used in the field of business analysis to maximize profits. This can involve predicting which products a customer is additionally interested in, depending on the items they have already placed in their shopping cart. To do this, the algorithm is trained using customer data that has already been recorded and derives if-then rules from this. As a result, association algorithms can be used to give the customer purchase recommendations or place products in a store in such a way that the customer is encouraged to make further purchases. The list of methods in the field of unsupervised learning is long. In addition to clustering and association, these include dimension reduction, anomaly detection, and autoencoders as further examples. Methods of supervised and unsupervised learning can also be combined. In this case, we speak of semi-supervised learning. Semi-supervised learning is always suitable when too little labeled data is available for supervised learning, for instance, because labeling is very expensive. Reinforcement learning. In reinforcement learning, we speak of an intelligent agent when we refer to the machine learning model. This agent observes a defined environment and interacts with it. A reward function is decisive for the development of the agent during training, through which the agent receives a reward based on its interactions with the environment. You can think of reinforcement learning as being based on the trial and error principle. In many interactions with the environment, the agent gathers experience iteratively. If it behaves in a goal-oriented manner, it receives a reward. If it behaves unfavorably, it receives a punishment or negative reward. The agent gradually learns to adapt its behavior so that it receives the greatest possible reward. Small strategy games, such as tic-tac-toe, are particularly suitable for familiarizing children with the idea of reinforcement learning. The environment, and therefore also the agent's interaction space, is limited to the playing field. The state of the game changes with every move made by the intelligent agent or the opponent. Depending on which moves the agent decides to make and which game strategy the opponent pursues, the agent wins or loses. If the agent wins, it is rewarded. If it loses, on the other hand, it is penalized. This evaluation is based on the rules of the game and the assumption that the agent should learn to win. Although this form of learning does not require any labeled training data, several prerequisites must be met before an agent can learn interactively from its environment. The following tasks represent the most important challenges when implementing reinforcement learning. 1. The setup of the environment in which the agent moves. Each state and the effect of a decision in each state must be defined. 2. Choosing the right strategy for the agent to achieve the desired goal. 3. the design of a reward function to convey the desired learning goal to the agents. Reinforcement-based learning is particularly suitable for tasks that require close interaction with the environment, such as in robotics for autonomous vehicles and chatbots. Good to know the difference between correlation and causality. AI derives knowledge from training data. During training, it processes large data sets like images or audio to recognize patterns. In supervised learning, labeled data, for example dog or cat, help it associate patterns with categories. AI does not follow predefined rules but learns independently by detecting correlations. Unlike humans, AI lacks intuition and true understanding. It relies solely on training data and cannot distinguish between causal relationships and coincidences. For instance, it may associate a specific pixel pattern with cat without grasping actual feline traits. This limitation makes AI prone to unintended biases in classification. Let's stick with the example of cat pictures. Imagine that all the cat pictures were taken by one photographer and all the non-cat pictures were taken by other photographers. The photographer of the cat pictures has added the company's logo to all photos. In this case, the AI may learn the logo as the decisive feature for the cat picture category instead of recognizing cats based on stature, whiskers, and head shape. In the context of the training data, the photographer's logo is a reliable feature for cat pictures. AI cannot be blamed at this point as it has no understanding of the task itself. For example, an AI cannot distinguish which features are responsible for assigning input data to a certain category and which features only occur simultaneously by chance. This shows how causal relationships differ from correlations. Therefore, please consider. Causality describes a relationship that is causally linked to an effect. The correlation describes a relationship that is statistically related. This relationship does not have to be causal, but can also be purely coincidental. ML workflow. We have explained the different types of ML. There is a danger that inexperienced ML developers very quickly and euphorically fixate on one type of ML and one algorithm that they already know. They train it directly with the data they have at hand, but often with little success. A structured approach to developing an AI model that starts much earlier is therefore far better and more promising. This also results in a much higher degree of traceability. The ML workflow presented here is based on ISO IEC TR 29119-11. The workflow for developing an AI model with ML includes various process steps and activities. As you can see, the workflow starts with the initial considerations about the goals of the model and extends to the deployment and monitoring of the model in the operating environment. Although the workflow is very complex, we have simplified it here. In practice, at the end of each activity, you consider whether it was successful. If this is not the case, you go back to one or more activities to improve it, working your way towards a successful ML model in iterative steps. Now, we take a look at the activities in detail. Understanding the goals. What sounds like a matter of course to some is often not so obvious to others. The project team should therefore at least ask the following questions and know the answers. What purpose does the ML model serve? Who are the stakeholders? What are the business priorities? What must the ML model be able to do, or what are the acceptance criteria, such as the expected accuracy or precision? Knowledge of these and similar aspects makes it possible to make the right decisions for most of the following activities. Selection of an AI development framework. If you know the purpose and objectives of the ML model, you can select a suitable AI development framework for it. Developers are rarely completely free to choose such a framework. In most cases, certain tools, for example for configuration or data management, are already predefined in a company. This can severely restrict the choice of AI development framework. One of the fundamental decisions in the machine learning workflow is the choice of algorithm to be trained in the subsequent activities. An understanding of the purpose and objectives, the agreed acceptance criteria, but also the type and quantity of available data play a major role in this. Depending on the AI development framework, developers can usually retrieve the selected algorithm as finished program code from a library. Otherwise, they must first code it and then possibly compile it. If an algorithm is available as C++ source code, for example, it may still need to be compiled specifically for the processor used for training. In the later phases of the workflow, the project team may find that even a carefully selected algorithm does not ultimately lead to the desired success. They then return to this activity and select another algorithm that they hope will produce a better result. Preparing and testing the data. This activity is one of the most important steps in machine learning, as the data prepared here forms the basis for all activities in the model generation and test phase. The type, quantity, and preparation of the data depend in particular on the previously identified objectives. The preparation of the data itself consists of four main activities: data procurement, data pre-processing, characteristic determination, and exploratory data analysis, also known as EDA. Model evaluation. After training a model, it must be evaluated whether the resulting model is good enough. A separate validation dataset is used for this. In most cases, one looks at the functional quality characteristics achieved, such as adaptability or correctness. For more information about the quality characteristics, please watch our other video that is listed in the video description and the comments. Evaluation is an important and at the same time sensitive step in model generation, as it determines whether a model meets expectations, should be trained further, or even discarded. For this reason, just like in the subsequent tuning, a careful and controlled approach should be taken, and each step should be documented in a comprehensible manner. We know from practical experience that several different algorithms or models, such as decision trees, SVMs, which are support vector machines, and neural networks, are often trained in parallel to compare them with each other during evaluation. They compete against each other as if in a contest. Tuning the model. The evaluation results are used to change or tune the settings for the next training of the models. These settings can be hyperparameters of the model, like the depth of a decision tree or the number of neurons in a neural network, or even the training algorithm, such as the number of training epochs or the learning rate. This model generation consists of the activities of training, evaluation, and tuning, which are carried out iteratively in this sequence. Test the model. Once the model generation is complete, an additional test of the fully trained model follows. At this point, being fully trained does not mean the model is ready for production, but the model will be evaluated using the metrics in the next step of the AI workflow. To do this, the functional performance metrics are looked at again, this time with an independent test dataset that has not yet been used. In some projects, the term holdout dataset is also used. This can be used to determine whether the model was adapted too much to the training or validation data during generation. If the functional test results when testing the model are significantly worse compared to the results of the model evaluation, this means that model generation must be restarted with a modified model, maybe using different hyperparameters of the model or a different algorithm. If the functional test results meet the requirements when testing the model, the project team also examines the non-functional characteristics of the trained model and the metrics of the training itself. These are, for example, the computing time required by a model to derive a prediction from the input data, the memory required by the model to make predictions, and the time required to train the model. Again, for more information about the quality characteristics, please watch our video. These types of tests require expert knowledge of data science or data engineering, knowledge of non-functional testing, and AI expertise. Therefore, they are usually carried out by data engineers, data scientists, or testers with the relevant know-how. Model provision. Successful model development does not mean that a model can be put into operation immediately. In many cases, the model still needs to be adapted to the planned target environment. And in some cases, the model may even need to be extensively redeveloped. The reason for this is usually a significant difference between the development and target system environment, such as the processor architecture, the memory requirements, or the required processing speed during operation. AI development frameworks normally support these steps. During the actual deployment, maybe in a cloud environment or on an embedded system, any necessary resources or a data pipeline suitable for the target system are put into operation in addition to the fully adapted model. A model provided is often only part of a larger AI-based system. Do not forget to test the integration of the model just provided with non-AI components. These can be conventional integration tests, for example. If the data transfer from the pre-processing steps of the image data, like scaling, cleaning, normalization, to the ML model is checked. Further test stages, such as system or acceptance tests in the larger overall system, may also be necessary before the provision of the model can be considered complete. Model usage, monitoring, and tuning are crucial aspects to ensure the effectiveness of AI models. A provided model, which is usually part of a larger system, can operate in very different ways. Some models, such as image processing algorithms in a camera system, run in real time and process the input data immediately. Other models may run in batch mode and only execute processing jobs at specific times. In practice, AI models are often used in changing environments. Over time, the detection of unwanted spam emails will no longer recognize new types of fraudulent emails as well, or may sort out too many harmless emails as spam. For instance, the AI-based spam filter will no longer meet the requirement for correctness. With regular tests and up-to-date data sets, testers can detect these deviations from the expected results. Using this knowledge, developers can adapt the model to the changed situation with extended training. To monitor the operational model, it can be evaluated at regular intervals against the applicable acceptance criteria, like the evaluation during the model generation. If a result deterioration is observed, developers can take various tuning measures depending on the algorithm or data used. Now that we have introduced the different types of ML in detail, let's look at the most important criteria for choosing the right ML type. In some situations, this is not obvious. It is therefore important to take your time, as the choice of ML type has a major influence on whether the trained model is suitable for the problem. You can ask yourself several key questions, the answers to which will help you make a sensible choice. To give you an overview, we have presented the key questions in a highly simplified decision tree. If there is a specific problem that you want to solve with an ML approach, the first step is to be clear about the available training data. Both supervised and unsupervised learning require a dataset for training and testing. This dataset must be sufficiently large and representative. Reinforcement learning, on the other hand, requires an entire training environment with which the ML model can interact. In contrast to unsupervised learning, supervised learning is characterized by the use of annotated data in the training. In the area of supervised learning, we essentially differentiate between the tasks of regression and classification. If the assignment of the annotations is numerical and continuous, such as the amount of rain to be predicted or the purchase price of a house, it can be a regression. If, on the other hand, the assignment of the annotations is discrete and categorical, such as the amount of rain to be predicted as dry, drizzle, rain shower, or the animal species dog and cat, the classification may be appropriate. Regardless of the type of supervised learning, correctly annotated data must be available, otherwise the AI will learn incorrect information. In contrast, unsupervised learning does not use any annotation of the data. Here we distinguish between two main types of ML: association, for ungrouped data with co-occurring relationships and dependencies, and clustering, for data to be grouped by similarity. We have summarized which key questions are important when deciding on an ML approach such as clustering or regression. However, this is not the end of the preparatory considerations because the ML algorithm or learning algorithm, the basic structure, and the ML model's hyperparameters must also be selected to suit the problem. There is no universal approach for selecting the optimal ML algorithm or the optimal hyperparameters. In practice, various aspects are therefore considered, which can be collected and discussed in a brainstorming session with stakeholders and experts, for example. Some aspects that should be included in the considerations are presented below. What is the required functionality? As in every development project, at least the basic requirements must be formulated at the beginning, so that the core functionality is defined for the selection of the ML algorithm, among other things. For example, the number of classes for classification or the value range for a regression must be defined to be able to specify suitable hyperparameters for the output. Which quality characteristics are required and which are of particular importance in the specific problem. The selection of quality characteristics is project-specific and can also include generally valid non-AI specific quality characteristics in addition to the AI-specific quality characteristics. Here is an exemplary selection of repeatedly relevant quality features. Accuracy. To achieve high accuracy, a complex machine learning algorithm often has to be selected. It should be noted that more accurate models are often more computationally intensive and therefore slower in training or later use. A balance must be struck between the complexity of the model and the available resources. Resource utilization. It is not always possible to provide as much computing and storage capacity as required as the AI component, for example, as an embedded system is part of a technical system. When selecting the algorithm, you must always keep an eye on the available resources. Speed of training. The more complex the model, the longer the training usually takes. Depending on how flexibly a model needs to be adapted to new requirements, regular retraining of the model may be necessary. Here, a less computationally intensive machine learning algorithm, a simpler model architecture, and cleverly selected hyperparameters can significantly reduce the training time. Speed of prediction. The speed of prediction can differ significantly from the speed of training. The speed of prediction is essentially determined by the complexity of the model and the resources available in operational operation. If the finished AI software is part of a real-time system, it may be necessary to work with machine learning models that require a particularly short prediction time, requirements for transparency, interpretability, and explainability. Some algorithms are inherently explainable, such as decision trees, if you want to use algorithms that are not inherently explainable, such as neural networks. Approaches from the field of explainable AI, XAI, can be used. However, it should be noted that the use of XAI can influence the structure of the machine learning model and the speed of training. What type of data is available for training the model? There are machine learning algorithms that are particularly suitable for certain types of data. For example, there are machine learning approaches that are specially optimized for processing image data using convolutional neural networks, or CNNs, or for processing time series using so-called long short-term memory networks, or LSTM networks. How much data is available for the development of the machine learning model? Depending on the algorithm, more or less data may be required. Assuming machine learning algorithms require more data to learn many details and complex patterns, then you have to deliver more data. It should not be forgotten that in addition to the training data, a meaningful dataset must also be kept as test data that are not used in the training phase. If the amount of data is not sufficient for the requirements of the algorithm, overfitting to the too small dataset can occur. How large is the input data? The greater the number of features in the input data that the model is to process, the more computing power must be available for the machine learning model. On the one hand, the speed of the model suffers under detailed input data with many features. On the other hand, detailed input data can achieve a higher accuracy that could not have been achieved with a smaller number of features. Consequently, when choosing a model, its complexity, accuracy, and speed must be weighed against the number of features. In addition to the model parameters, the number of features in the input data can also be reduced, for example, resolution of images. What output do you need? Not all machine learning algorithms can be trained equally well on the desired output. For example, when selecting a clustering algorithm, the expected number of classes for clustering must also be considered, as some models may be unsuitable for problems with more than one class. That is not a simple yes or no decision. Are there empirical values from similar problems? There are often already projects that have dealt with a similar issue. Research is worthwhile and can reveal solutions that have not yet been considered. Could this be successful? Often there is only a guess as to which machine learning approach might be the correct solution for the problem. An exploratory approach can then be chosen. True to the trial and error approach, some ideas have to be checked to find out whether they represent a promising solution approach. In our experience, it is particularly important to incorporate findings from other projects with similar issues and to be brave enough to try out approaches. A simple prototype can be very helpful to check whether an approach or idea is worth pursuing further. If a model is trained using machine learning, it must be repeatedly assessed during this training whether it has been sufficiently trained. For this purpose, we introduce the two terms overfitting and underfitting, which play an important role here. In the beginning, the model is still undertrained and not adapted to the training data. If the training is aborted in this phase, we speak of underfitting. Ideally, the error rate in the prediction decreases with each further iteration or epoch, and the model adapts more and more to the training data. If the model has adapted too much to the training data, we speak of overfitting. A so-called validation data set can be used to monitor the learning progress. This is withheld from the model during training and is only used to determine the error rate in the prediction of the model. This allows you to observe the extent to which the model has already adapted to the training data. In the following sections, we examine overfitting and underfitting in greater detail. How can they be recognized? Which models are particularly at risk of overfitting and underfitting during training? We speak of overfitting when the model has adapted too much to the training data. The trained model is then unable to recognize the basic correlation or pattern in the data. As a result, the model loses the ability to generalize and later apply what it has learned to new data. You can think of it like us humans. If we study one source on a topic for too long and in too much detail, we may lose focus on the relevant topic content and become too fixated on that respective source and its details. It's like knowing the way from city A to city B via various highway interchanges by heart, but if a highway is closed, you're lost and don't know any alternative routes. Models that are trained with a small dataset are particularly susceptible to overfitting. There is then a risk that the actual pattern cannot be derived from the training data. Complex models are also more prone to overfitting than models whose complexity is appropriate to the context to be learned. If the model is too complex, there is a risk that the model will even adapt to random fluctuations or noise in the data, or to individual outliers. We speak of underfitting when a model has not been sufficiently trained. The model is immature and does not reflect the fundamental relationships between the input data and the results. In contrast to overfitting, underfitting models deliver poor results with both the training and validation data. In addition to training being terminated too early, the type of model selected can also be the reason for underfitting. When selecting the model, developers must ensure that the model can recognize the patterns in the data. In an underfitting model, model assumptions have usually been made that do not reflect the complexity of the patterns in the data. For example, if a linear model is used to train a nonlinear relationship, the model will not be able to learn the underlying relationship and will produce inadequate results regardless of the length of the training. Another cause of underfitting can be an inadequate training dataset that does not contain the features needed to establish the basic correlations between the input data and the results. This may be due to the selection of features or an unfavorable selection of the training data set. The model will then not make accurate predictions even with the validation data. If underfitting is present, the training data and the model selection must be carefully re-evaluated and questioned as to whether the model is even capable of learning the desired correlation.